Welcome to this video. In this video, I will be discussing regarding data processing inequalities. So this will be like a series of videos. I will be preparing 3 to 4 videos concerning with the proof of data processing inequality, Fano's inequality, both in the classical case, and I will also be discussing a few of the quantum implication. And so let's see. So data processing inequality is a very fundamental inequality concerning information processing and transmission of information. So the point is you cannot, as you process your information, you cannot increase the amount of information compared to what you already had. So it can be understood like suppose if you have a phone of suppose 80 megapixel, and then you click a image of some monument or something, and then what you do is you try to send this data to other phones. Suppose from 80 megapixel phone, if you try to send it to a phone which is very old, like suppose it has 8 megapixel camera processor, then you will see that automatically the vividness of the data that is stored in your 80 megapixel phone, it would have been significantly depleted. Or in other hand, if you try to send it to suppose a 108 megapixel camera phone with a better processor, you won't see your photo to be as much vivid as a photo directly clicked by this higher megapixel camera. So in some sense this is associated with the fact that as you process the data, as you send it from one phone to another, the other phone, this is like a communication which either causes loss of data or at most can keep it same. So more precisely, this is based on Shannon's communication scheme. So what we do in this particular scheme is that we have some sort of a message, and then we encode this message in a signal. Like you click a photo and then encode it in the phone itself, encodes it in terms of this pixel size, which are nothing but this matrix of 0 and 1. And then what you do is that you send it via suppose electromagnetic waves traveling through vacuum or air, and then your other phone, it receives the data and then it unpacks it from 0, 1 to the proper pixels, and then it will show you the photo. So there is a step of encoding, transmission, receiving and decoding. And the basic idea is that the step of transmission or step of decoding doesn't care which kind of photo you sent. I mean, it will equivalently decode a photo of suppose a mountain or a tree or a concrete, anything. So the idea behind data processing is that of Markovity or memorylessness. So suppose we have X, Y, Z. These are these three. So basically you have encoded the message and you are transmitting. What is a Markov process XYZ if the probability of happening of Z, so Z is a random variable, probability of happening of Z, so capital Z equal to small z, given you have fixed values of X and Y, only depends on Y. So this is the fact that it doesn't matter which photo you are sending. Only thing matters is the encoding, only thing matters is the transmission process or Y. So this is in general most of the cases true, and particularly these channels that we see which are transmitting these data, they are what we call noisy channels. Now what this means is that you specify a noisy channel if you just provide the conditional probability distribution. So suppose what is the probability capital Y will be small y given capital X as small x. This is what we call as a noisy channel, this probability distribution, and it maps from the set of random variables that X can take to the set of random variables that Y can take. And similarly you have W2 explained in the same fashion, and this set of random variable where the variable is mapping, or the output of the process is called the alphabet. So with this understanding of Markov nature, we try to understand some of the properties of Markov chain, or this is also called memorylessness. And in a deep way, this is also connected to fact of thermodynamics, if you think, in the sense that as you start processing your data is somehow either decreasing or remaining fixed. Is like as the time flows, the entropy of the universe either increases or it can stay same in adiabatic processes. So there is some sort of a deeper relation with thermodynamics. So now let's understand this Markov process. So in general, if you have a set of x1 to xn random variables, you can say that the set forms a Markov process if what happens is that for every step, for all n greater than equal to 3, what happens is that probability of getting that step only depends on the previous step. So you see, you drop all these random variables, just keep the previous step. And now what we can say is that there is an equivalent criteria of understanding Markov process. It is given that probability of z given x and y can be written in this particular form, like probability of getting x, y and z divided by getting x and y. And for this to be finally equal to probability of z only dependent on the previous input, we need this sort of a separation of this joint probability distribution x, y, z like this. So here this is the equivalent criteria that the joint probability distribution factorizes in this kind of a nice form, that what is the probability of getting x and getting y given x and getting z given y. So at every time there is a sense of memorylessness associated. So now given this particular criteria, what we can do is we can prove another important equality between these probability distributions, that is probability of getting x and z given y. So it is like given a particular kind of an transmitted encoding, what is the probability of getting z to be the decoding and x to be the original message. So, and it turns out you can again write it like this and then use this equivalent criteria. So you will see that what we can write from here to here is that probability of y given x times probability of x, and there in the denominator we have probability of y. So this entire thing is nothing but probability of x given y, because let's try to see, because probability of x given y is probability of getting x and y divided by probability of y, and probability of getting x and y is simply equal to probability of y given x times probability of x divided by probability of y. So you can see that here is a bit of reversal of the fact, because probability of y given x can be written as probability of x and y divided by p of x. So anyway, so the important point is this particular result. So given a particular encoding, probability of the original message and the final decoding is what we can say is conditionally independent. So the point is, they can be anything. Like this is just the manifestation of the fact that Z doesn't depend on X, whatever you do. So this is what we call as conditionally independent of the present state of the register, and this is equivalent to the fact, like in case of in English language, you can say yesterday is a history, tomorrow is a mystery, and today is a gift. So basically they are in a sense conditionally independent. So now we move on to one more important property, and that property is the fact that if x, y, z is a Markov chain, z, y, x is also a Markov chain. How do we verify that? We just simply verify probability of getting x given y and z. It should finally be probability of getting x given y, because a Markov chain just need to satisfy the memorylessness criteria. So what we do is that we take this expression, write it in this particular form, and then use this p, x, y, z can be broken into this particular form, because x, y, z is a Markov chain. And then what we do is that, let's see, from here to here what we do is that we just write pz given y as pz comma y divided by p of y. So we get a factor of y, and now we can see that this p of y will cancel, and p of x times p of y given x just p of x and y divided by y. So this is just, so the point is, given x, y, z a Markov chain, z, y, x is also a Markov chain. So that's all for this video, and in this video we discussed about this Markov chain. Particularly I would like to now give one of the example of what these noisy channels are. So noisy channels are nothing but this conditional distribution, classically speaking. In quantum mechanics they will correspond to these CPTP maps which take you from one density operator to another. But classically, one of the nice example is that of a noisy typewriter. So suppose you have a typewriting device that prints A, B, C. So suppose you have a typewriting device that prints A, B, C up till let's see, say Z. And what it does is, it is noisy in the sense it either, when you type A with a probability half, it goes to A, but with a probability half it can also go to B. Similarly, B can go to C or D. Similarly, C also. Basically, Z can either go to itself or it can go to A. So basically, it goes to the next of the process with a half probability, and then it inherently will introduce noise, because if we try to print suppose A, B, C, then sometimes it will come out to be correct, but sometimes what we can get is BBC, or we can get BCC or BCD. And another interesting fact with this noisy typewriter is that now you can guess that what we can do to get a maximum information out of this is that we can get a maximum information when we can print characters like A, C, E, G, like only the consecutive characters. Because then what will happen, even if this noisy typewriter introduce some noise, like A can go to A or B, or C can go to C or D, checking the output string, you can get what the input string was. Because you see, suppose it went to something like B, C, F, G. Then you know that because you are printing consecutive characters, because there is a B, it can only be possible that there was an A. C goes to C, F shouldn't have been there, so only thing is that it can be E and G will be there. So in this sense, you can given 26 English alphabets, you can transmit 13 of them exactly. So this is related to something called as channel capacity that we might discuss later. So that is given by log 13 base 2. So that's all for this video. In this video we discussed Markov process, noisy channels, and some of the properties of Markov process. In the next video we will try to look at what data processing inequality means. We will give some of the understanding of chaining rule of conditional probabilities and mutual information.